Okay, thank you very much. So first, I would like to thank the organizers for the invitation. It's always very nice to be here at Fields. And the rest of the talk will be dedicated to thanking Bob Moody for, in some sense, having shaped infinite dimensional Lie theory in such a way that I think we can do with some objects, namely Kac-Moody groups. We can prove some results which I think they were not, for which they were not designed. Okay, so the running question will be this one. What is exotic Kac-Moody theory good for in discrete group theory? And I will try to explain to give some more context. But the first level, I think, for to answer this question is the level of Lie groups. Already. Let me recall briefly what what I mean by Kac-Moody theory. So Kac-Moody Lie algebra is defined, say, over C, basically thanks to a generalized Carter matrix. CN for short, say A, which is a finite matrix indexed by a finite set S by convention, which is defined by a Serre type presentation. Okay, and the point is that the resulting Kac-Moody Lie algebra is what belongs to the class of more general class of Lie algebra with triangular decomposition. Which is the name of the book written by Arturo and Bob. Okay, and one of the important points is that we still have root spaces which are permuted by a Coxeter group, again called the Lie group, and there is a recipe to define this Lie group. In the recipe we can produce, so let's call it W. W is defined by an explicit Coxeter presentation. Namely, if we call AST as before coefficients of the Carter matrix, the generalized Carter matrix, then out of this matrix we can cook up another now symmetric matrix by the following rule. We look at the product AST ATS. We look at the, and according to whether this product is 0, 1, 2, 3, or is at least 4, we decide that the corresponding coefficients will be 2, 3, 4, 6, or infinity. And the resulting Lie group is the group generated by symbols S, those which index this matrix. And we, as for any Coxeter group, the presentation only prescribes the order of products of two elements. And of course, the statement is that if MST is infinite, we don't prescribe any order. Okay, so it's already nice in the sense that in general. Sorry? Yes, but I think it is contained. Well, okay. I don't know. Yeah, okay, right. In general, W is infinite. The exception corresponds to a classical Carter matrix. Okay. So what I will mean by exotic, first we'll consist in forgetting classical cases, of course, but I will also kick out another class of Coxeter groups, namely the affine Coxeter groups, which is the first, the less wild infinite family of Coxeter groups. So exotic will mean neither spherical, finite, nor affine. And now what I want to mention in this first section is the fact that we can already single out among infinite Coxeter groups, say irreducible Coxeter groups, we can single out the affine Coxeter groups by purely group theoretic means. And this is illustrated in the following. This is illustrating in many ways, but I think the most striking basic elementary statement is the following. It's due to say Noskov, Margulis, Noskov, Lindbergh. It was proved in 2002, I think. Let W be any Coxeter group. Say irreducible. To avoid any ambiguity. Let H be a subgroup of W. So I don't even assume it's a Weil group, it's any Coxeter group. Let H be a subgroup. Then either H is virtually abelian, or it contains a finite index subgroup subjecting onto some non-abelian free group. So I think you know this result in a more general context, but with a weaker dichotomy. This is Tit's alternative. You know, Tit's alternative is the following statement. If you take a finitely generated linear group of matrices, then either it's virtually solvable or it contains a free group, non-abelian free group. Then if you restrict to a Coxeter group, then you have this stronger dichotomy in the sense that virtually solvable becomes virtual abelian, and containing an abelian free group becomes stronger in the sense, in this following sense, which is called big in group homology. Okay, so now if we go back to Weil groups, this has a strong consequence. This statement has strong consequences on the shape of root systems, which was already seen algebraically, but I like to present it this way, to present this dichotomy this way. Consequence of root systems. So by root systems, at the moment, I mean the set of real roots. here sets of real roots in Kac-Moody algebras. So what's the, if we go back to Weil groups, if we are back to Weil groups in Kac-Moody algebras, we see that whenever a Lie algebra is not affine, an infinite dimensional Lie algebra is not affine, then its Weil group has exponential growth. This is how you can read this, okay? Whenever an infinite dimensional Lie algebra is not affine, its Weil group has exponential growth. The question is, what are the consequences on the root system? So to answer it precisely, I should introduce the terminology on roots. And I should already use a geometric viewpoint on roots. Okay, so to answer this, we adopt the geometric viewpoint on root systems. Namely, it means the following. So in principle, a root is a linear form, but we, up to some losing a little bit of information, we can identify these linear forms with their non-negative half spaces. And this is how I will see roots there, okay? So we see roots as half spaces in a Euclidean in a real vector space. It's cones if I want to be more precise, but I won't use it. Okay, and if I want to show, if I want to illustrate this statement, I should say the following. We have two basic examples of infinite root system to have in mind for my talk. We have two examples of root systems to have in mind. Typical example. First one is classical one. I will call it this way: classical or affine. Typically A2 tilde. If I look at the root system seen as set of positive half spaces, half plane, consists of spaces bounded by walls, and the walls are the lines which appear in this tiling. Okay, so I will write a root this way plus this double segment to indicate which half space I choose. So typically, the root system for A2 tilde corresponds to the half spaces bounded by the walls on this tiling. This is what I call the classical example. Now we go for exotic examples. And this was the first, I think, striking observation for Kac-Moody groups. It's the fact that some val group, some available val groups in general Kac-Moody theory look like this. Namely, I take my favorite negatively curved geometry, typically H2, hyperbolic plane. And for any integer at least 5, I can draw a right angle regular argon, provided I have at least 5 sides. And the tiling corresponds to the tessellation obtained by extending the edges and reflecting the tile. Okay, so this is typically, this is with my geometric viewpoint on the fine on root systems. If I reflect my tile, I get some other walls. And in this case, the main observation is the following. Main observation, there are lots of configurations of roots like this. I have a root here, I have a root here, and the third one here. And the boundaries of the roots are pairwise parallel, but they don't give a single parallelism class, which is something you will never see in an affine tiling. Okay, and okay, you may think it's specific to this tiling, but the truth is that for any non-affine infinite root system, I can produce many configurations like this. And this is a crucial tool if you take into account the definition of Kac-Moody groups and commutation relations between root groups. This is very crucial to see the difference between affine Kac-Moody groups and non-affine ones. Okay, so this is what I wanted to say. Already at the bigroup level, there is a sharp difference between affine and non-affine infinite Kac-Moody groups. Any question? No? Okay, so now we can turn to discrete groups. This is the second part. What Kac-Moody theory brings to discrete group theory. And now for this, I have to face, well, I have to mention one of the main problems in Kac-Moody theories, which was solved by various people. Typically, how to integrate Kac-Moody Lie algebras. Okay, in the sense that I want to define groups whose tangent space at the unit element would give me the Kac-Moody Lie algebras, which are defined by generators and relations. So it was a difficult. It is a difficult problem, which was first, I think, considered by Moody and Theo in the early 70s, and the outcome was of this attempt of this proposal of definition was a family of groups with remarkable combinatorial properties. Namely, existence of what is called the Tite system or Bien pair. Of Tite system, Bien pair, this is the same, with Lie group W as before. So I won't make this sentence more precise, except that a TIT system, it's a purely abstract group theoretic set of axioms, which was designed by TITs to prove uniformly projective simplicity of rational points of isotropic algebraic groups, simple algebraic groups. So this is what Philippe mentioned in the first talk this afternoon. Okay, to my knowledge, I think BN pair is the only way to prove uniformly simplicity of rational points of simple algebraic groups, projective simplicity. Okay, so TITs designed a set of 4 axioms purely in abstract group theoretic terms. And the question before was that he classified the spherical ones, namely those with finite Weil group. He knew that some Weil groups could be affine because he was, at the moment, he was constructing Bruatti's theory on the theory of semi-simple group over local fields. And Kac-Moody groups, whatever the version of group Kac-Moody groups you take, they have to produce new TIT systems, new BN pairs, these nice combinatorial structures. But now you have much less constraints on the Weil group you can obtain. Namely, it only needs to be crystallographic, which means that the coefficient of the Coxeter matrix have to be 2, 3, 4, 6, infinity. This is why I recall the recipe to cook up M out of A. Okay. So it was very exciting. I guess it was a very exciting for TITs at the moment. And now I will explain that some constructions of Kac-Moody groups were made closer and closer to algebraic group theory. And the groups I use are those which were defined by TITs in the late 80s, which is the closest version to Chevalier group schemes. Which goes as follows. The starting point is, as for Chevalier's group schemes, it's a generalized Cartan matrix, which is not enough if you want to define reductive groups, even in the classical case. You have to add plus, you have to add information given by 2 dual Z lattices, which will prescribe the shape of maximal split tori, size of maximal split tori. And I won't be more specific, but we call this datum consisting of a generalized Cartan matrix and 2 Z lattices in duality will be called the Kac-Moody root datum. And let me provisionally write such a datum by this curly R. Okay, so what TITs does is the following. To each R, each TITs attaches a functor, say G. We will forget dependence on R at some point. From rings to groups. This functor is defined by generators and relations. Its weakness is that it has no algebraic geometry structure. It's defined such a functor in such a way that when you look at the generic fiber, which is a pedantic way to say when you evaluate G over C, you get more or less the automorphism groups of the complex Lie algebra. plus some other axioms which I will not mention. But the point is the following. Whenever I'm given a generalized Cartan matrix plus some mild additional information, I can cook up a functor. And now what is good is that I can evaluate this functor on any field. And what is proved in the same paper by Tits is that whenever you evaluate this functor on a field, then you get a BN pair. A Tits system with the val group you expect. Okay, so fact. Fact. For any field, okay, the group G of K, which I will call lambda for because K will soon be a finite group, and I want to see G as a discrete group. So for any field K, the group G has two twinned BN pairs. Okay, so again, this is the nice same. This is the same nice combinatorial structure, providing, in classical case, providing simplicity. Okay, at least in the when the val group is finite, say. And what I mean by twin is the fact that the group is so nice that it has two collections of subgroups satisfying the Tits axioms, and these collections of subgroups do not carry the same information. This corresponds to the fact that in general the val group is infinite, so you have no longest elements in the val group switching positive and negative roots. So we have to have two Tits systems in some sense. Okay, so typically, a bad example for me, which was very good in previous talks, is the following. It's classical case. So, okay, let me call it bad in my context. Bad example. Loop groups, sorry. So typically, if you consider G, you take your favorite Chevalet scheme, Chevalet group, you evaluate it on K on Laurent polynomials with coefficient in K. This will not be a Kac-Moody. It will be a Kac-Moody group, provided you do what Vladimir did this morning. You go back and forth between polynomials and coefficients of polynomials. So this is GR of K for some affine Kac-Moody datum. And I have to explain why I consider these examples are bad examples for group theory. This is bad because this is for me, it's a linear group. And I have nothing to expect to produce new phenomena from the viewpoint of discrete groups. So it is unfair, but hopefully not in my talk. Typically, these groups, the obtained group, the affine Kac-Moody groups are finitely generated and linear, and by a result of Maltsev, they are residue finite. Which means that if I take the intersection of all finite index subgroups, or equivalently all finite index normal subgroups, then I obtain the identity. So it means that I have a lot of normal subgroups. Yeah. No, I always mod out by center. I don't think so.
Example, you have precisely all K points of this group, or it's extension?
Ah, okay. You have okay. This is the same question as Olivier, maybe more or less connected. It's extension, but you think extension will not give nonlinear groups? Okay, but okay, but it's kind of fake nonlinearity, if I may. Yeah. No, okay, well, I should make it, you are right, I should make it more precise. Residue finite for me, it means that you have you have a huge amount of finite index normal subgroups. So in particular, you're not simple. And I'm interested in simple group, infinite simple finitely generated group. Okay. Is it this way? It's correct. Okay. So now bad examples are given by a fine group from my perspective, namely cooking up some simple finitely generated groups. When if you get bored with Kac-Moody theory, here is a problem: how to produce infinite finitely generated simple groups. It's not so easy actually. It was solved by in the mid-50s by Higman, I think. Without okay, so let me state the first result I would like to mention to answer my running question, so to speak. It was a result proved by Pierre-Emmanuel Capras and myself in, say, 2006. Let lambda be a Kac-Moody group, be an irreducible. So I have to be careful with my assumption. Simply connected, whatever it means this is more or less what Philippe said, generated by root subgroups, even in this context. So I take an irreducible, simply connected, non-affine Kac-Moody group over the finite field FQ. And I assume that FQ is large enough with respect to the general scatter matrix, which is mild. Assume that Q is large enough. And this is mild because, for instance, Q bigger than the size of the Cartan matrix is enough. So it's completely explicit. Then lambda divided by its center, which is finite, is simple and finitely generated. Okay, so this is really, I think, the one first satisfactory answer to the question. Kac-Moody theory is a kind of huge algebraic machinery to produce Lie algebras, groups integrating these Lie algebras. And you can do representation theory if you want, and then this is what David Hernandez explained yesterday, typically. You can stick to the affine case and have some Galois theoretic, interesting Galois theoretic questions like what Vladimir and Philippe explained. But you can also forget the affine cases and do less technical things in some sense, but to produce some the kind of results which are more relevant to discrete groups. Yes. To work over a finite field? No, I think it's an open question. I think if Yoon is listening, I think it makes sense to ask the question for infinite fields. I know how to do it because, okay, let me phrase it this way. This assumption Q large enough will tell you that this group is a lattice when you embed it diagonally in the full automorphism groups of the two buildings in taxon. And if Q is large enough, I can see, so if Q is large enough, I can see lambda as a lattice. And I can use, instead of using an algebraic machinery to prove simplicity, I use Margulis theory. And I mimic what Margulis did for the normal subgroup theorem for higher rank lattices to this case. And recall that the normal subgroup theorem by Margulis says that if you take a lattice in a higher rank algebraic group, an arithmetic lattice, then any normal subgroup has to have finite index. So to speak, it is half simplicity. But it is completely true. And you can mimic this even in the affine case. This is what is interesting in the proof, I think. You can mimic Margulis and prove this normal subgroup theorem. Whatever the Kac-Moody group, the finitely generated Kac-Moody group, provided you can see it as a lattice, provided you have this condition typically, you can prove the normal subgroup theorem and rule out infinite quotients. But it works perfectly well with SLN FQT T-1. SLN FQT T-1, provided n is at least 3, it has finite quotients, a lot of finite quotients. No infinite quotients, but a lot of finite quotients. And the trick is to use this configuration of roots, strange configuration of roots, which disappeared, sorry. In the non-affine case, you use the defining relations of Kac-Moody groups plus existence of such configurations of roots to rule out existence of finite quotients. And for this, you really need to be in a non-affine situation precisely because you want this kind of configuration of roots. I'm sorry to be short about this, but this is not what I wanted to mention in detail. But at least I think this is the first argument to convince that even exotic Kac-Moody theory is an interesting topic. Okay. So now I have to be a bit more precise. This is still an algebraic, in some sense, the statement here and the conclusion of the theorem is still an algebraic statement. It is simplicity for groups, but we can make it more algebraic up to considering buildings. We can go further, provided interpret existence of Bn pairs geometrically. And this was known to Tits from the very beginning. Existence of Bn pair for a group is completely equivalent to, for a group G, say, is equivalent to existence of a transitive, very transitive, we'll make it more precise later, a very transitive G action on a building. And this is what I have to explain. A building is some very specific geometry. So to define a building, I should first say, as a first approximation, I should say that a building is a union of tilings whose geometry is governed by a given Coxeter group. And you impose some incident axons on the copies of the given tiling you chose from the beginning. Okay, so let W be fixed. W acts on the tiling, a generalized tiling. So, sorry? Yeah, exactly. This will be apartments, yes. So if I fixed W, then my Coxeter group acts on a generalized tiling. So you can see that there are various, for a given tiling, which is called a Coxeter complex, which is an abstract simplicial complex. You can choose, what is nice is that you can choose various geometric representations. So in Bob and Arturo's book, they choose the Tits-Cone realization. But what is nice is that in geometric group theory, it was proved that you can choose a nice non-positively curved metric space, cellular complex. And what is nice is that what you have in addition to, with respect to the previous representation, it's no longer a cone, but then you have non-positive curvature properties, and eventually you get fixed point lemmas, interesting fixed point lemmas for group actions. So, okay, so have in mind the A to T tiling or my Fuchsian tiling as before. Okay. So let me call sigma the Coxeter complex. Then by definition, a building of type sigma or of Y group W is a cell complex union of copies of sigma called apartments so that first any two cells in my complex are contained in a suitable copy of sigma, in a suitable apartment, not unique. Okay, so whenever I have a geometric problem, I have to consider a geometric configuration only involving two points. I can consider it's an elementary geometric problem in the sense that it lives in the copy of some tiling. It lives in some apartments. And there is a dual axiom in some sense, which is for any two apartments, say A prime, there exists an isomorphism, cell isomorphism, tiling isomorphism, if you want, between A and A prime. Not a big deal because I assume that each apartment is isomorphic to sigma, but the point is that this isomorphism fixes the intersection. It takes into account the way the apartments are embedded in the whole space. Okay, so it's a bit, this is the only list of axioms I chose to write down today. It's a bit hard to swallow in some sense, but let me sell the axiom this way. I want to do geometric group theory. This is cheating. This is not the original motivation, but still. I want to do geometric group theory. I want a metric on my space. Okay, and assume that any sigma has a nice metric, W invariant metric. This is the case for affine buildings, and if you have this example in mind, you're also convinced I have a negative Lie curve metric here, and I want to make it global. I want to define a metric on the full building, let's call it X. I want to define a metric on X whose restriction to any apartment is the initial one. Yes?
Do you assume that the intersection of this apartments is a subcomplex?
It is a subcomplex, yes. It will, yes. It will be convex even. Okay, so the first axiom tells me that I have a candidate for the distance because whenever I'm given 2 points, I can take an apartment containing them and compute a distance. Okay, this is for candidate for distance. And the second axiom, up to some work, will tell you that the distance you compute in any apartment containing the pair of points will be the same. So the distance is well defined. Okay, intuitively, this is what the buildings are designed for, up to having a metric motivation. Okay, so before going to topological groups, let me say, but I have to use buildings for this anyway. So to rephrase existence of twin BN pair, of twin BN pairs in Kac-Moody groups, I can say the following with formulation of existence of twinned Tit systems in Kac-Moody groups This is the following. For any Kac-Moody root datum, for any field, if I define lambda to be the k-valued points of Tits functor on the field, then this group lambda has acts strongly transitively on the product of two isomorphic buildings, say x minus plus x plus. And these buildings have the expected Y group. This Y group W. So from the perspective of geometric group theory, this kind of result did not belong to the standard corpus of knowledge of geometric group theory, but it's in some way a way to rephrase this result is the fact that due to Tits is the fact that if you take this algebraic machinery, which is Kac-Moody group functors, whenever you take a field, then you're in, for instance, a finite field, then you get a geometric situation with a product of two geometries with nice symmetries plus non-positively curved metric, non-positively curved distance. So it fitted at the moment in the early in the late 90s, it fitted perfectly with Gromov approach to discrete group theory. Okay, so it's so moreover, if K is finite, then X plus minus is locally finite as a cell complex for a suitable non-positively curved distance. Sorry, I should say metric realization. And the space are even complete. So this is what I wanted to explain for discrete group theory, right? You have the simplicity statement. This was the first step. And you have this geometric viewpoint so that any Kac-Moody group evaluated over a finite field is a group acting on the product of two non-positively curved buildings, locally finite if you start from a finite field. So again, I have to assume finite field because I want to mimic Margulis. Okay. So at this stage, this is what I wanted to say on discrete groups. Now I will be a bit shorter on topological group theory. So I should say that after this 2006 result, there were other results which are more relevant to geometric group theory. Namely, as I told you, if, sorry, I didn't say this, but if you assume that that A is nice in such a way that if you assume that the Coxeter matrix has no infinite coefficient, this is what it's called two spherical. If you assume that A is two spherical, and if you assume that Q is large enough with less explicit bound, what you get is finite presentability of the group. It's not even finitely generated, but it's finitely presented. And if you assume that Q is even larger, then you have Kasdan's property T, which is a well-known property for discrete groups, which is very useful in rigidity theory. So it was really a good idea to develop Kac-Moody, exotic Kac-Moody groups. Okay, so this is what I wanted to say on this. And okay, there are other results saying that you can say, okay, if you're doing geometric group theory, you can be a little bit skeptical and say, okay, but now, you know, in geometric group theory, we classify finitely generated groups geometrically, metrically, by means of Cayley graphs. And there is another family of nice, simple, finitely presented groups, which is due to Burger and Moses, and in which the groups are less complicated, so to speak. They act co-compactly on product of trees. It's better because the geometry is less mysterious. The problem is that from the viewpoint of classification in geometric group theory, these groups are all quasi-isometric to one another, meaning that they are in loose B-Lipschitz equivalence from the point of view of Cayley graphs. If you weaken a little bit B-Lipschitz equivalence by allowing additive constant, then all the groups you produce by considering these co-compact lattices in product of trees, they're all in the same class. But if you consider Kac-Moody groups, then you produce infinitely many metric classes, quasi-isometric classes of finitely presented simple groups. Okay, so now I want to mention the last contribution of Kac-Moody theory to, I would say, less algebraic group theory. So for this, I stick to this example. We keep our group lambda, which is the FQ points of a Kac-Moody Tits group functor. So this guy acts diagonally on two buildings, two locally finite buildings. This means that from the group theoretic viewpoint, I can see lambda, this is as a discrete subgroup of the full automorphism group of the first building cross the full automorphism group of the full isometry group of the second building. But I said that if I choose a finite field, then this building is locally finite. So for the compact open topology, these groups are locally compact. Okay, so these are locally finite. Then I get a diagonal embedding of my Kac-Moody group, which, as I said, has no structure from algebraic geometry. But this guy lives as a discrete subgroup in a product of locally compact groups. So, and what we independently prove, Lisa Carbonet, Howard Garland, and myself, is that if you take Q large enough, so this is always discrete, and if you take Q large enough, then okay, lambda is discrete, but it's big enough in the sense that it's a lattice, meaning that the quotient of this group, this product group, by this group carries a finite invariant probability measure. In some sense, if Q is large enough, this Q is at least S, is bigger than S, sorry, then this is a good discrete approximation of this product of groups. Okay. So again, the example you may have in mind is the inclusion of SLN of FQT_T-1 in the product of the two natural completions of FQT_T-1. Example, take this inclusion. Okay, I can complete with respect to T and T-1. But for my purposes, this example is not so good in the sense that it is linear. It's a linear example. It's a matrix example. But this is perfectly fine in any case. So the idea is now forget one factor and make lambda act on a single building. Then the action is no longer discrete. So it makes sense to take the closure of lambda in the full automorphism group. If I take lambda in the full automorphism group of one of the factors, then something really happens. And this is called, I get a much bigger group, and this is called a completed, geometrically completed smoothie group. And the question again is, to what extent this group in general is close to this linear example, this linear specific case. And so the last result I would like to mention in this vein is the following theorem. Lambda bar, as above, is a locally tropy group, P being the characteristic of FQ, which is topologically simple. And even abstractly simple. This is a result due to Misha Hershov in 2008. Okay. But of course, we know that whenever the generalized Cartan matrix defining lambda is not affine, lambda bar will contain lambda mod z lambda, mod center. So it will not be a linear group because it contains a non-linear. So locally, it means that any point admits a neighborhood consisting of a tropy group. Yeah. It's exactly, you know, this is, it mimics SLN FQT. This is the best you can do, provided you know that your groups will not be matrix groups, I think. Okay, and still you have abstract simplicity, provided, of course, the Dynkin diagram is connected. And okay, so now we get, in some sense, we get nice topological groups. So the question would be to play, so if I may, to play McDonald's game and try to do some harmonic analysis on such groups. And the first result is a bit disappointing in the following sense. Now go back to my first section, Weyl groups. You know that whenever the Weyl group is not Euclidean, it is big in the sense that it virtually subjects onto a non-abelian free group. So the intuition is the following. What did Satake and McDonald do? They proved that if you take an algebraic group, a non-Archimedean simple Lie group, it acts on a Brüatzitz Euclidean building. And if you take a good maximal compact subgroup, which always exists, then the convolution algebra of by k invariant function is commutative for convolution. This is the starting point of spherical functions. It tells you that you have a Gelfand pair. And when you have a Gelfand pair, you have Fourier transform Planck-Shell formula. This is very nice. And McDonald made the spherical function completely explicit and completely algebraic. Again. The starting point, if you want to mimic this theory, now you are stuck in the following sense. Go back to the strong Tits alternative and select a non-affine irreducible Coxeter group. Then you see that, okay, what was good with affine Coxeter groups is the fact that they are virtually abelian. And actually, it corresponds to commutativity of convolution for by k invariant functions. And what Jean Lécureux proved 10 years ago is that whenever W is infinite non-affine, there is no Gelfand pair in lambda bar, whatever the compact group. So there is no way to prove Satake results, which existed since 63 for in the affine case. Okay, so this is in some sense some geometric contribution, negative contribution to the field. But the point is that recently some guys like Auguste Hébert and Ramla Abdelatif proved that it's, so to speak, algebraist revenge on this topic, since I did my best to make everything as less algebraic as possible, as you understood. But this is, so to speak, algebraist revenge, showing that there is a nice Ecole theory for even for complicated multi. A nice Ecole theory for lambda bars, the groups lambda bar. And what is even nicer is that, you know, what I did not mention is the fact that when Tits considers his group lambda, he has to forget the imaginary root, which is a big deal in Kac-Moody theory. But once you complete the groups, then imaginary roots, so to speak, are back. So you may think it's not a good news. It's not good news because you don't like imaginary roots for multiplicity reasons, for instance. But it's very, very good news when you want to have to understand commutation relations between root groups. Because once you complete, you have nice unique writings properties for commutators. Okay, so I will stop here. Thank you.